Everyone, so either you're going to be very energetic or very sleepy. I'm going to try and hopefully get everyone a little energetic. My name is Raphael. I am the CTO of Quantum Insights. My role is primarily to work with a variety of our clients, really get them to understand how these different new emerging technologies can apply to their organizations, let them understand how the technology works, break down their use cases, and find out how we can apply these technologies for their organizations. This has gone all the way back since blockchain, if you guys remember that, back in 2016, 2017. We are now doing it with AI, and we're even starting to work with some of our clients regarding quantum computing. My presentation is going to have a slightly different tone. Everyone else that's talked to you before has talked about the wonders and the beauty of quantum computing, how we can address, as Usman mentioned, preventive diseases, treat Alzheimer's. We've talked about how it can be applied to physics to unlock essentially the next frontier. Mine's a little darker. Right now, what we're seeing is everyone says, well, quantum computing isn't coming for 10 years. There's nothing that we need to do right now. And the answer is that is completely false. What we're starting to see is some of our foreign adversaries and other bad actors, they're collecting our data, which are currently encrypted in methods that quantum computers can break. So the goal is, if we take this data, we collect it, 10 years when these computers are available, things like your bank statements, things like if you own Bitcoin, those logs are going to be broken. If you have secure emails, if you work with organizations like the NSA or other secure government agencies, they're going to break into your emails and understand the traffic that you send in the future. Right now, not tomorrow, not next year, and God, not in the next decade, today, we need to start thinking about upgrading our cryptography ways so that way they're ready when quantum computing is in reality. And that's what we want to talk about today. Now, before we do that, let's talk a little bit about what cryptography is. So, in short, everything we do on the web has some form of encryption. If you send an email, we don't want everyone in the world to be able to read or understand it or whatnot. We put some form of cryptography or encryption on that data. When you send text messages, when you have bank transactions, when you have anything online, that data has some form of cryptography or encryption to protect it. So that way, only the people that are meant to see it can understand the data. Everyone else that tries to monitor the traffic isn't fully able to understand what it is, what's inside of it, and what's going on. How are we able to do that? Well, in short, math, very complex math, but math in a very specific way. You want math that is really easy to generate in one direction, but very difficult in the other. So there's a few ways that we do this. The first that we do it is something called RSA. We take two really big prime numbers and we multiply them together. You get a very, very, very large number, and from there, when you unlock it, you need to know one of those prime numbers. If you don't know it, it's very difficult to do. So how about this? Let's go through an exercise. I have, behind my parking ticket, a $10 Starbucks gift card. Okay, so here's the deal. I'm going to give you a prime number, and just a large number, and the first person that can tell me what two prime numbers make it up gets the gift card. Okay? Don't worry, it's easy. You can use your calculator. You can use ChatGPT. When you know the numbers, go ahead and shout it out. No. 1 and 13, not quite. I'll give you hints.
7 and 9, 89.
Who said that? Come on, if you give your Starbucks gift card. There you go. Now, there is another opportunity for a Starbucks gift card. This one's $20. This one's a little tougher. So I'm going to give you guys, get your ChatGPT ready. We're only going to spend maybe 15 seconds on it this time. We don't want to waste too much time. So go. Starts with 1. I think it ends with a 7. I'm just joking with you guys. So in RSA, what happens is we take essentially prime numbers that are about 250 or longer numbers, and we match them together and we get this monstrosity. Not even computers can figure out what the two prime numbers are in this situation, right? So what happens is, if we were trying to brute force this and have a computer go one by one by one to find those prime numbers, it would take millions of years. If you do a rough estimate, no lie, the sun would die before you were able to brute force this calculation. This is why RSA in particular is so secure, because trying to get the prime numbers out of this number is so stinking hard. But if you have the two original numbers, it doesn't even take a second to compute this really large monstrosity. That's the concept of our basic cryptography in the US right now, or just in the world right now, is that we want to have math that's really easy in one direction, but really hard to walk backwards. Now we talk about RSA, it uses a form of math called integer factorization. There's another one called ECC. I'm not going to get into it because that's a little bit more complex, but the main thing to note is that it uses a slightly different type of math. It uses something called logarithms. And again, I'm not going to go into it because we'd be here for 8 minutes and I'm going to lose everyone's interest and I have no more Starbucks gift cards. So, now, before we talk about how cryptography and quantum go together, I want to just do a quick recap in case there's anyone here that's new about quantum computing. What are the basics, right? So there are three main principles, and we've talked about this before. There's superposition. In classical computing, we have bits, which can typically be a 0 or 1. Quantum computing has something called quantum bits or qubits. They are essentially 0 or 1 kind of at the same time. It's a very hard concept to grasp, but I want to put it like this. You guys ever just drove up, you get to a stop sign, you're trying to make a left turn, and you see the road in front of you doesn't have stop signs, they have the right of way. So what are you supposed to do? You're supposed to look left, and then right, left again, it's clear, you make a left turn. How many times, this happened to me on the way here, which is why it's very fresh, using the example, you look left, there's no car, you look right, there's no car, you look left, you're about to go, car zooms by. Okay? Look right, car runs by. Start over, okay, look left, look right, look up, son of a, and then you do this for 5 minutes, the car behind you is beeping, it's a real pain in the butt, right? Quantum computing, the concept is, what if you're able to look left and right at the same time? What if we're able to digest that information, and using that, we could have gone right away, because we would have seen in the first 2 seconds when we're wasting time looking in both directions, the area is clear, we can go. Now, let's hold this metaphor really quickly. Do you think that having the superpower of looking left and right at the same time would make you a safer driver in all circumstances? I probably already know, right? If you're going down the highway, you're on the left lane, going 70 miles per hour, do you think looking left and right would make you a better driver? I would argue it might do the opposite. You have so much information that you're digesting that you actually might be slightly unsafe. If a car brakes right in front of you, why is looking left and right going to help you with it? So there's this misconception that quantum computing can be applied to just about everything. And it's going to make everything better. My MacBook's going to be a quantum computer. And I already argued this. Quantum computing solves one specific type of problem really, really well, or multiple types of problems really, really well. But in an ideal scenario, in our future, quantum computing and classical will work together to each solve the problem that they are the best at. Okay? So hopefully that clears up a little bit here. Now, there's two more processes. I'm going to zoom through them a little bit. They're a little bit complex. But first we talked about interference. We've explained it as a way where we focus on the correct answers and kind of ignore the noisy or the wrong ones. Well, how do we do that? Well, if you see these two examples here, we have constructive and destructive waves. If you look on the constructive side, you'll notice that there's a bump there. There are peaks on each of these graphs that match up. The dips on these two graphs line up. When you merge them together, you get that bottom graph where the peaks and the dips are very, very exaggerated. These are called probability waves. So the probability of this being the correct or the right answer is high, it's certain. At the same time, we have something called destructive, and it's the very opposite, where the peaks of one line match the dips on the other. You merge them together, you get a flat line. What happens when we apply that to our quantum scenarios, we use that to essentially get rid of what we deem as noise or incorrect answers. And this principle of probability waves, interference, is essentially how we're able to always make sure we pull out what we believe is the correct answer, right? Imagine, these are probability waves. The probability of something happening, or what you're certain to, is high. Finally, entanglement. We talked about this as well. Imagine you take two qubits, they're the best of friends. But the thing is, they also are very aware of each other's value. So the way that I like to describe this is equals, imagine I have one box of red rock and this other box of blue rock. They never leave my desk. But the moment I open one box, I automatically know it's in the other because there is no, there's no gray rock, there's no orange rock, it's only red and blue, right? So I seal both of them up. I ship one to China. The moment I open up mine, I know that the rock in China is the opposite color. So if I open up to China and I see the red rock, I know I have the blue rock, and vice versa. That's essentially entanglement. In a sense, it's how we ensure that qubits are able to communicate with each other, and that's how we're able to help solve these really large, complex problems. So, we talked about quantum 101, talked about cryptography 101. How do they merge together? Well, this one slide, I remember I once gave a lecture in front of a bunch of Navy colonels and admirals, and they did not understand words, so I'm just going to zoom over this in 5 minutes at a very, very high level. So, there was an individual named Peter Shor. 1994, he was doing experimentation and came up with an idea. What if we apply a different type of quantum computing on the integer factorization problems, and it's able to find those prime numbers in a really quick amount of time? And the way he came up with is this. We have a computer with enough qubits where it's able to compute every single possibility at the same time. And what we do is we apply something that he named the quantum Fourier transformation. And what happens is it's a different mix of interference and entanglement, where in short, it cancels out all the answers it believes is wrong, and it retains the ones that it believes are right. It does a little bit of extra factorization, and at the end of it, you essentially get the right answer. Now, when we talk about if we were trying to brute force those prime numbers and those really large numbers, it would take millions of years. It's feasibly impossible to do that, correct? The reason Peter's Shor's algorithm is so important is because it no longer makes it impossible. When you're able to compute everything at the same time and then apply his form of interference, that Fourier transform on those numbers, those results, you essentially are able to find the result, those prime numbers, in a very reasonable amount of time. We don't have ideal benchmarks because we obviously don't have computers quite that large yet, but the fact of the matter is, we're able to do this in the future. The question is when. When are we going to be able to have the computers that are large enough? Because the moment that happens, every single type of computer, every single encryption that utilizes these current encryption models, these cryptographic models, they're broken. Everything we do online, banking transactions, crypto transactions, your medical healthcare records, that's going to be visible.
Don't say that.
Oh, it's scary, isn't it? So, before we talk and get everyone a little scared, let's talk about the current reality and the future, right? We've had a lot of examples of quantum computers talked about today. I want to focus primarily on Google and IBM's because right now they're primarily leading the charge in the sense that their largest computers are in the low 100 qubit range. Now, sounds like a big number. Can we start to apply Shor's algorithm? The answer is absolutely not. If we wanted to get a rough benchmark of how many qubits we would need, what we do is we take the key size of most of our RSA algorithms. It's about 2048 bits. Okay. The current benchmark is you take that number, you multiply it by 2, and that's roughly how many qubits you would need to calculate every single possible permutation. So in this case, we're talking about roughly 4,100 qubits. Give or take a few extras in case there's errors or whatnot. I am not a mathematician, but I'm pretty confident 4,100 is a little bit bigger than a little over 100. So we still have quite some time before these computers are ready. That being said, there's a few other things we need to focus on, right? So first off, these computers have incredibly low coherence times. What is that? We're talking about the delicate state of quantum mechanics where we're trying to get two states at roughly the same time. It's a very delicate art, very delicate science. Right now, these computers are able to hold this state in milliseconds, sometimes seconds. But with Shor's algorithm, we're talking about trillions of possibilities at the same time. We don't need seconds. We need something able to hold that state for a much longer period of time. If not, we're not able to finish the algorithm in time, right? So that is, besides the number of qubits, something we need to work on, is just how long we can hold these superposition states. Second, the error rates, which you talked about, also needs to be addressed. These qubits are prone to errors, and that is something that Google has made significant progress on, But it's still, again, after a few seconds, these computers become very error prone. So the technology is still, I would say, at best a decade away, but it's still something to be aware of. And the last thing I want to mention is, if you've been following the NVIDIA trend and whatnot, you'll notice that a company called D-Wave got into just a hedge match with the CEO a little bit because they were dissing quantum computing and whatnot. So if you did some research, you would have known that D-Wave is a quantum computing company, and they have a quantum computer which has about 1,000 qubits. Oh, that's way closer to 4,100, you may ask, but the computers function significantly differently, and why many of the people that are currently researching physics are not utilizing these computers. These D-Wave quantum computers, they are able to utilize superposition, but the way they use interference and entanglement is significantly different than what we need. So these computers are primarily utilized by organizations for optimization problems. So think about organizations like UPS or FedEx. They have a route. Okay, what is the optimal way to plan this route so that way our driver covers this in the least amount of distance, saves the most gas, and makes the fewest number of stops? If you're trying to do that with a classical computer, it's incredibly difficult. But the D-Wave computer, given the way that it is built, is very suitable for these types of problems. However, Shor's algorithm and many of the problems in biology, physics, etc., need a different way of interference and entanglement than these computers are currently capable of. So while yes, the D-Wave sounds very scary because it has 1,000 qubits, I wouldn't focus too much on that. If anything, that one actually will be really good because maybe your package from FedEx will come a little bit faster today. So let's talk a little bit about what the threat impacts us right now and what I alluded to in the beginning. What we notice is a variety of bad actor organizations and foreign entities are slowly collecting data from sensitive organizations. For example, we found out that a foreign entity was approaching a variety of government organizations and pulling back encrypted emails and communications that were not fully blocked off. We also found a few bad actors that primarily are targeting the medical industry were pulling back encrypted EHR records from certain people. And there's many other organizations doing something similar for banking transactions, banking information, and other things, right? What's happening is these folks are realizing that the moment the quantum computers are available, that data becomes available. You can crack into it whenever you have the computers ready. Now, in many ways, we joke that 60 years from now, is your email to Uncle Tom going to be bad? Probably not. But the communications at the NSA, probably yeah. Your medical records, do you really want that public in 10 years? Not really. What about your banking transactions, your banking information? Still probably not, right? So what we need to start thinking about doing is upgrading our cryptography to be quantum proof now. Because if not, these organizations are going to continuously harvest our data in the hope that in the next decade, they're able to crack this and they find really good information. And you do not want to be one of those few people. So, how do we do that? Cryptography right now is based off of, I would say, two broad categories. There's symmetric, there's asymmetric. The way to consider this is using keys. Symmetric, there's a single key used to unlock and lock, right? Simple. Asymmetric, you have two keys, one to lock, one to unlock. The reason why you would do this is because over the web, you don't necessarily want to share and give people your key, right? You want to have your key for your own information. So if you don't want to transmit the key, how are you able to lock it and have someone else unlock it using their own key? And that's how asymmetric came about. The issue is, asymmetric is heavily reliant on things that can be broken by Shor's algorithm. Integer factorization, that RSA we talked about, ECC, which is discrete logarithms, all those are very prone to Shor's algorithm in the future once the computers are available. So right now, what many organizations are trying to do is find different cryptographic methods that are more immune to quantum computers. There's a few, and I don't want to bore you with the details, but right now the three leading ones are essentially something called lattice-based. Imagine a very, very high dimensional space, like say 200 dimensions. What is the shortest path between those dimensions? And that is essentially your key. That is very hard even for top-of-the-line quantum computers to do. Code-based, similar. You inject a variety of errors into your code. It's really hard to pick those out, even with quantum computers. That's why that one's a little bit immune and hash-based. So everyone hopefully knows a little bit about hashing, especially for the crypto crowd. It's essentially an algorithm that turns something into a very long, complex sequence. What hash-based essentially is a series of trees that you have to find the correct hash. And that is also very immune to quantum computers at the moment. I know this is very technical, and I'm trying not to be, I'm very sorry. But ideally, what organizations are trying to do is replace a lot of these RSA and ECC encryption models with these different alternatives that we mentioned before. Symmetric, very different story. It uses permutations. Permutations, for whatever reason, are really kind of not really involved with Shor's algorithm. So if you have essentially a symmetric algorithm that you're using for your encryptions, for your cryptography, all you have to really do is double the keys, and that'll make it quantum proof. So the issue is, not many people use purely symmetric, so we don't really talk too much about this one. But for very small, essentially small labs, small organizations, where it's just, I'm trying to secure my own data, it's a very easy upgrade for these organizations. So let's talk a little about timeline and what we can kind of do right now. So what I'm doing with a variety of our organizations and clients is we first do an audit. We want to work with every single person to understand their cyber team, how their cryptography is set up, what functions are they using, where are they using it, how is the data stored, etc. When we have this audit, we can then start to say, okay, these are the primary systems that you really want to start focusing on and making sure they're secure. These are the secondaries, these are the tertiaries, et cetera, right? Then we can start planning how we can start upgrading these systems to be quantum proof, right? The most common method that we're starting to use with a variety of organizations is called a hybrid method. So this is something the NSA is currently using, and funny enough, Google Chrome just rolled this out a couple of years ago. What they do is they take the encryption from your standard asymmetric, you take your quantum proof encryption, switch together, and then you have your new encryption. It's very simple, and the reason why organizations do this is because we can't fully test the quantum proof encryptions because there's no quantum computer to run it on to validate that it fully works. So in the case that quantum computing becomes more real, we can test that algorithm, upgrade it over time. But at the same time, we're not fully trusting it and letting current computers break those encryptions as well. So that's essentially the first step for most of these organizations that we're working with, is building out these hybrid solutions. And that's normally where we try and encourage folks, especially in sensitive industries, again, like the medical industry, banking industries, et cetera, to start focusing there. Do those audits, try and find the primary systems and data sources, and then try and build hybrid solutions around them to protect them immediately. In the case that you have these foreign and bad actors, try to pull and steal your data in the case of, again, trying to steal and break into it in the future. So that's pretty much it. If there's anything, one major thing I would like to really leave with everyone here today, it's that we kind of take the fact that these computers are 10 or so years in the future. We take advantage of that. In many ways, that is the wrong outlook, right? I want us to look back at AI where it was maybe 10 years ago. No one really heard about LLMs or transformer models. But the moment that ChatGPT 3.5 came out, everyone scrambled to get involved. Then Google came out with a big one. Grok, that was a big one that came out of nowhere. Llama, everything. The investment poured in once it was shown it was viable. And that is historically what happens with most of the emerging technologies. The moment that we see something viable, there is a huge rush to invest and build it out. And I have a feeling that quantum computing is going to be very similar in the next 5 years. Google or IBM is going to cross another milestone, and the computers that we think are a decade away might only be 5. So we need to take this seriously. We need to start thinking about our own security, our own protection, understanding our current cryptography, and start making actionable plans today on how we can better protect ourselves by upgrading our current methods. And that is it. Thank you so much. Please. Oh, we're going to race around with microphones.
Yeah. said something that I hadn't heard before, that some of these encryption schemes require a quantum computer to verify the security of them. I thought, they're all subject to mathematical proofs, and maybe that we haven't been able to prove it mathematically, but are you saying it actually requires
It does.
a computer to?
So a good thing with most theories is we can come up with the math to prove that it should work 99% of the time. But there's that 1% of the time where we say, oh, it actually doesn't work in these circumstances. Good science, good math always requires a little bit of in-person testing to do. So we're very confident just based off of our theorems, our mathematical proofs, that these models will work. But there's another thing. We prove the math works. Are we building out the math correctly? We built the house with its architecture correctly. Are the contractors putting up the beams using up-to-code regulations? So until we're able to really bring out quantum computers and really poke at these things, we're never going to be sure if our current designs are viable.
As a metrologist, that's what we would call end-to-end calibration.
Exactly.
Okay.
Exactly.
I just want to say you're a really good teacher.
Oh, thank you. Am I a good teacher because I bring Starbucks gift cards? Is that it?
No, like you actually sat and broke it down, and that was very well done.
Thank you. All right, well, if there's no other questions, we can have a quick break before we jump into the panel. Thank you all so much.